So it's 1:35. Seems like people are still trickling in. So I'm going to tell the people that are here the answer to the midterm number 4. No. I don't even know what number 4 is yet. Okay. I want to pick up where we left off last time. We were talking about trajectory optimization. About the midterm, I guess, actually. The goal is to have the midterm cover the topics that are up to this lecture. So next Tuesday's lecture will still be content. It will add to what you've learned, but they will be sort of extensions of the kind of things we've already talked about. So it'll not quite be a review, but it'll be a additional thinking about these kind of topics. Yeah. So has it been announced yet or not? Yeah. So we've pushed it to Friday, so that you don't have to feel like you're studying or doing P-sets. But I would encourage you to do it before Friday, to the extent that that makes sense, because it will help you with the material that will be on the midterm. Yeah? And also, the project proposals are due after spring break. The goal was to have you think about it over spring break. Good. And I think, Sava, did you announce your review session yet? Tuesday, 7 to 10. Room information on Piazza. Yeah, thank you. Any logistics questions? Most of the logistics we'll post on Piazza and answer on Piazza, but yes?
You guys were going to propose a project with Spot, right? Do we still need to write a project proposal?
Yes, please. Yeah, it'll help us coordinate those things, and it'll help us even decide which environments are most important for us to provide well and things like that. The first version of the project proposal is don't feel like that's a total commitment. I would like you to think about it enough that it could, that it could be a viable project, but that's a chance for us to give you feedback and help align scope and other things. Awesome, let's dive in. So we started talking about trajectory optimization, right? Last time, even for linear systems, we thought, I hope, fairly carefully about a few of the different transcriptions, right? So we have our mathematical problem, and we want to transcribe that with a finite number of decision variables into an optimization problem. So when we were talking about the direct transcription, we wrote, my decision variables are both x and u, right? And I'll minimize, for instance, my running cost. Maybe I have a final cost. And then I'll explicitly write in my dynamic constraints. I'm typically going to solve this just from a single initial condition. That's not always necessary, by the way. Sometimes you actually have a final condition. You're trying to figure out what a good initial condition would be that would get you to a certain place. There's flexibility in what you choose there. You could have a set of possible initial conditions or things like this. And then a bunch of other constraints. For instance, maybe you have something like a input limit or whatever, okay? That was our direct transcription. And then we also talked about direct shooting, which took the observation that if x0 is known and u is known, then you could just effectively step your simulator forward here to solve for x. So don't actually need x as a decision variable. It's completely defined by equality constraints. So you could just solve that away. And that would be a min over only u of the similar objective. And this was solved as a function of, it was written as a function of u. And I won't write the whole thing again, but the point was the direct shooting sort of solves away the x decision variables by substituting in the equality constraints. I then, in my examples, I leaped to continuous time. Let's just make sure I say that step carefully. So this is very natural in discrete time. I've got a discrete set of times, a fixed set of variables. So I've got a finite parameterization of my trajectory in that case. So how did we go for continuous time? Well, the simplest thing to do, which is actually a very common thing to do, is to use the exact same direct transcription, direct shooting methods, but just make the discrete time approximation, use a numerical integration method of your choice to basically make the f out of your c. So for instance, this could be written as this is like my time step here. This would be the Euler integration approximation. And you could put in other integrators in there. If you had a second order integrator, a fourth order integrator that you particularly liked, you could still write that. You could figure out, given a fixed, held u of n, right? That's like the zero order hold was the modeling assumption, or some assumption on what u does between n and n plus 1, right? Then you could write out the integration law and still have your parameters be a constant set of, a fixed size u, fixed size x, and impose whatever fidelity of integration and accuracy constraints you want to impose. Typically, the trajectory optimization, it's much more expensive than simulation, right? So it's like simulating many, many times while you're doing second order gradient descent, right? So a lot of times you will see integration accuracies much, much lower in trajectory optimization than you would in simulation, right? You might do trajectory optimization with time steps of 0.1, but then you might simulate with 1 e to the minus 3 or something like that. So, which is interesting. One of the things we'll talk about today is stabilization, right? If you simulate back the trajectory you optimized with a coarse approximation, and you've changed your integrator, you might get something different than you expected. We'll say that again in a minute. Okay, so in general, there's this sort of recipe of going from continuous time to discrete time by writing the constraint as one step of numerical integration. What's interesting here, though, is once we go into the nonlinear optimization, we've already given up. If FC is not a linear set of equations, then this is looks like a nonlinear constraint in its general form, and we're going to be using nonlinear optimization. Then I've listed always x and u as an optimization, but you could actually do min over x, u. You could even put h as a decision variable, right? And then write these constraints. The time step could be a decision variable. In fact, sometimes people will actually have time steps that are different for every interval and allow the trajectory to stretch and shrink in time between these set points. Okay, now, once you do that, you have given the solver enough rope to hang itself. So you probably want to put some boundaries on that, like having time collapse to 0 is not desired. Having collapse, having it go, arbitrarily inaccurate is probably also not desired. So you'll often see when people do this, they'll say like, I don't know, something reasonable here. You could get very clever with this. You could actually put like a numerical integration error term that could constrain the upper bound on this, right? You could put like a different integrator as your error control on this. But good in theory, I rarely see that done. Okay, but that's actually kind of interesting. So in fact, do you remember what we were playing with in the double integrator case? If I make this big again. And we had our perfect discrete time thing, but it has this sort of slant there, right? We were paying some penalty because the true switching time didn't happen to be exactly on the boundary of our time discretization. But with a small change, if I use one of these transcriptions that has h as a decision variable, then actually you can get much, much closer. It's the way I plotted it makes it look like there's still a slant here, but the minimum time, which was 2.84 before, and we know the optimal solution, let me say it carefully here. Yeah, the optimal solution for the continuous time system, is 2.828. My discrete time without h as an approximation was getting 2.84. Depending on how much you care about time, that sounds like a lot or a little of an error. But if you allow time to stretch and shrink, then up to solver tolerances, you can get it to line up very accurately, right? And that's actually, depending on the optimization, maybe that's a lot worse for the solver. Maybe it's kind of a benign nonlinearity if it's only moving a little. Okay, so it does add additional modeling power, but it also it makes things non-convex again. Yes? Cut corners on concave curves. Say that again. Yep. I think you have to watch out for these things. So for instance, it's very common to, it depends very much on the situation, but it's very common to just use a single h or to otherwise constrain that h is the same at all times. Otherwise, it might try to put a lot of resolution in easy parts of the problem and then take big jumps across some of the harder parts of the problem. I completely agree that could happen. Yeah. So, and similarly, it can try to, divide time down to 0 to obtain very little cost in some parts. So I think you're right. You have to be careful when you do this. Mm-hmm. Yeah. Right. So the connection to numerical integration is actually pretty nice in some sense. So there's a whole field of error-controlled integration, right? So for instance, like the Runge-Kutta 4-5 method, you do a fourth order forward pass. You also do a fifth order update, and you compare the difference between the two. And you could like put a constraint on the difference, on the error, let's say, and you could make that a constraint on h. So there are advanced ways that you could put a bound on h that's roughly bounding the sensitivity of the accurate, of that. Yeah. So I think there are creative things. Nice. So there is one more transcription that is wonderful and different enough that I want to make sure you've heard it. And it's actually the one that I run most commonly. It's a little bit more directly, it's like this idea of trying to, what's the right integration strategy to put into my optimizer constraint? but it comes a little bit more natively from the continuous time. Okay, so this is like wedging the continuous optimization into the discrete time formulation. But there's kind of a slightly more natural, I almost said direct, but that is horribly overloaded in this lecture. And that is called the direct collocation method. Okay. Okay, this is the figure I made in the notes to try to explain it. But here's the idea. We're still going to do min over x and u, and we'll do our same kind of costs and constraints. By the way, if we have a discrete time or a continuous time x and in un like this, we might multiply this by h also, for instance, to get the leap from the continuous to discrete. Okay? And then the question is, how are we going to write the dynamic constraints? Okay? And the observation is, and it's really just, there's an interpretation of this as just yet another numerical integration scheme. But let me say it in this particular way. So if I've got x defined at all of these points, okay, and u defined at all these points, I also have the derivative constraints. I have x dot fc xu, okay. So if I've already said that the system is here, and I've got x and u defined, then it already says something about the slope of that line exactly at these points, okay, at the sample points. What's more, it says something about the slope of the line anywhere, okay. If I have an x here at this sample point, and another x at this sample point, and a derivative, I know the derivative here, and I know the derivative here, then that completely defines a cubic spline that goes through those points. Okay, those four numbers in one dimension defines a cubic polynomial curve. Okay, so for arbitrary x and u, because I need u to define the derivative, okay, I can just say I'm going to think about the curve here. But that doesn't say anything about the dynamics. How do you bring the dynamics in here? Well, you need to pick some other point, at least, on the curve and say that that also has a derivative constraint. Okay, so if I pick these collocation points, it turns out the sweet spot is to put them exactly in the middle of the time interval middle. Okay, and I say the derivative of this point is also has to match the dynamics. Then this is, you could think of it like a strange trapezoidal rule or something. It's a-causal in the sense that it's like semi-implicit in the sense that it looks at both points, okay? And it's even, because it's fitting a cubic spline all the way through here, you can think about it as a rich numerical recipe. But basically, it's defining a cubic polynomial given x, a first order hold given the u samples, and it's just constraining that the derivative of that curve matches the dynamics. Let me say that again. So given x and x dot at the samples, let me say it like this, at samples, it completely defines x of t as a cubic polynomial. There's only one piecewise cubic polynomial that can go through all those points with the slopes defined by x dot. And the dynamic constraints, I'll say, is that the x dot at the collocation points has to equal and that's the way I write my my dynamics. Okay. It turns out there's a sweet spot where x is a cubic polynomial and u is a first order hold, because then the value of x at the collocation point is easy to compute. Very easy to compute, okay? And that's actually the workhorse that we use most often. If you understand the direct transcriptions, right? It's almost the same as this. It's just writing the dynamic constraints slightly differently, where it has the entire curve in mind, and it's making a statement about the derivative of that curve, right? Yes? It actually, it's no less or more real time than the other, than the discrete time things. So you can absolutely just move this forward, do the receding horizon kind of control exactly the same way. It's completely robust to that. Only in the sense that optimal control is dependent on your future decisions. That's still true. But I should have said, I said it a little bit too sloppily, possibly. So if I have the x, and if I just have the decision variables associated with this segment, then that segment is completely defined. So it's not that there's like the decision variables over here are affecting the shape of this curve, only through minimizing the objective. So writing that, like writing out the mathematical program that sort of looks up the spline, evaluates the dynamics 2 times, computes the spline coefficients, figures out the collocation value, evaluates the dynamics 1 more time, and puts that as a constraint. It's not hard to do, but it's kind of annoying, right? And that's the kind of place where in Drake and in other solvers, we bottle that up. So you just say, I've got a direct collocation problem. And then you give it the system and the context, for instance, okay? And it'll write the mathematical program for you that has those dynamic constraints implemented. And then you'll see code looks like traj opt is a direct collocation, and then you can traj opt.prog to sort of get the mathematical program and add additional costs and constraints to it. And it also gives you easy access to variables that are associated with all the normal quantities that you might want to write a cost or constraint with. That's just the abstraction that the software layer can provide. Does that make sense? So all of the pendulum swing up, cartpole swing up, acrobat swing up, the examples that I showed yesterday, just because it's kind of my go-to, was with direct collocation, actually. I like it for many reasons, but one of the things I particularly like about it is it kind of makes a statement about how you should about the continuous representation. If I just do direct collocation, then I kind of still have a decision left to make about how do I interpolate between those points if I wanted to execute a continuous trajectory, right? This one is explicitly making a decision about the full continuous time parameterization and then writing constraints against that. As an integration, as a numerical integration recipe, it has 3rd order accuracy. It's like a 3rd order integrator. And it has relatively few evaluations of the dynamics for a 3rd order integrator. That's what makes it kind of a good choice. It's a pretty efficient 3rd order integrator. Make sense? Yeah. Yep. Yep. Yeah. So you can take the same idea and do something with more than cubic, and you could do more than a first order hold on U. The reason that this is kind of the nice spot is that when you have the dynamics as a derivative, first derivative, you have 2 points and their derivatives. That's a total of 4 numbers. The curve that is completely defined by that 4 numbers is a cubic polynomial. So it's sort of the natural choice. given the level of detail. So there are second order collocations. So for instance, if you know I have q double dot equals f of u, right? So you have a second order system. You could write a more refined, people have written more refined direct collocation methods which leverage the second derivative and put those constraints. I can't remember if they use cubic polynomials they probably use a higher order polynomial in that case. But it's just like the natural, the constraints that you have define derivatives, and with that number of decision variables and derivatives, the cubic polynomial is the natural parameterization. Good question. Yes?
So what you're optimizing over is not x at these points, but like at each point the polynomial.
What you say is true. He says you're optimizing over these curves. That is true. But one of the nice things about it is that decision variables are actually still the value that the trajectory takes at the sample points. So it's, in some sense, the decision variables are no different than if you were doing direct transcription, which is natural because you'd like to write your costs and constraints against the values of at the sample points. You don't want to have to think about all your costs and constraints in the coefficients of a polynomial curve, right? But the curve is completely implied by the sample points, and so you can also back out the curve. Yeah, good. Okay, we were talking a little bit last time about you're asking a bunch of questions about the solver interface. And let me actually, I think it's important to say one extra detail about that today. In the software, like what happens, it'll help you understand how the solver works, and it'll help you write better code, not just straight code. I think mathematical programs. Okay, so let's just think about what Drake does when I do add linear constraint. That's sort of clear. I can write add linear constraint. I can write it something like this. It will formulate an object which is the linear constraint, and it knows how to pass that to solvers, right? If I do add a quadratic cost or something like that, and I hand it something like this, it knows how to parse the coefficients of that and add it and keep it as an object, which is the quadratic form, and hand that to the solvers. It's interesting to ask, what happens when I do, this is add, by the way, add linear constraint, add, if I just say like add cost, right? And I say, I'm going to pass you some arbitrary function f. What happens there? Or if I do add constraint, and it doesn't have a prescribed form, what does Drake do in that case? Or what can any solver interface do in that case? And we said that the goal is going to be, for instance, to provide, if it's going to dispatch to a nonlinear solver, there's cases where we want it to still figure out and dispatch to a convex solver. But in the case where we want to dispatch to a non-convex solver, we said we're going to do second order programming. So it seems like we should have to pass, f, but also like partial f, partial x, right? And maybe even the second derivative. How the heck is that happening? Like, what is happening in the interface to do that? Because you presumably need those gradients to do second order programming, right? Okay, so what is happening in the code? So if you were to write, if you have like x equals prog dot new continuous variables, 2x, something like that, okay? And then if you were to write prog.add cost sine of x squared, let's say in Python, okay? That could be numpy sine or math sine, no big deal, okay? The thing that you get handed back from new continuous variables in order to pass it around, that's actually a symbolic variable. Drake has a symbolic engine behind it. So when you call sine of a symbolic variable or power on a symbolic variable, it actually turns this into a symbolic expression. I lost one of my pieces of chalk. So this will be a symbolic expression. Which you played with in the sums of squares world too, okay? And so when you call add cost with this kind of a thing, then it will, first it'll check to see if it's convex with some simple checks. You know, is it a quadratic form? Is it positive quadratic form? Is it linear? If it is, it will call add linear constraint for you, or linear cost for you. That's great. Okay, if it's not one of the easily recognized forms, then it just keeps around the expression. And every time you need the gradient, it does a little bit of work to take the gradients. Actually, the first time you need the gradient, it will cache the work it does to take the derivatives of that. Okay, so you can imagine if you have a symbolic engine and a symbolic form, you can get the gradients out of that. But you don't really want to do that for big expressions. Like if you don't want to generate the symbolic equations of motion for Atlas and then do it again for Atlas's end effector position and stuff like this. So super useful for like fast prototyping and nice clean code, but not super recommended for performance. There's another way you can do it, where you can say def, my cost in Python of x, and then it would return sine of x squared, let's say. And then you call prog.addCost my cost, you pass in the function handle, and then the decision variables that should associate with that. And this will use the callback, and the solver will actually, every time it's evaluating the cost, it'll call your method. Okay? And if you were to put a breakpoint here when it's calling, and you look at the type of x, if you're being called by one of the SQP solvers, for instance, then the type of x here will be an autodiff variable. Okay? So it's actually a variable that has the value of x, but also the gradients of x coming in. It's typically, depending on where it ends in your code, but it typically comes in with the gradients all initialized as the identity matrix. And then as it goes through here, every time it calls sine of x, it updates the nominal value, but also the gradients, just using the chain rule. And it's doing forward mode auto differentiation for you. Okay? So you don't really have to think about it. You can just call, the add cost of this function. It will take gradients as necessary to tell the solver about it. But you should know about it, even though that's convenient and it's meant to, so you don't have to think about it. You should know that it's taking gradients, because otherwise you could write things that are bad cost functions that have bad gradients, and your solver will fail, right? So, by the way, you'll never see it for SNOPT, for instance. You'll never see it try to take the second derivative of your cost, even though it's doing SQP. SNOPT, although it's making quadratic approximations, is only ever evaluates the first derivative of your function, and it uses the standard tricks to sort of make a second order estimate out of sequential first order evaluations. Is that kind of clear? I know that's like writing Python on the board, which is not awesome, but okay. So for the most part, if you're willing to solve non-convex optimizations, you get to just write functions that say these are my costs and my constraints. Good. But write functions thoughtfully, please. Right? So just as an example, let's say I want to constrain the distance of the distance between 2 points. Okay, let's say I want to have x minus x star. I'll say it like this. This is like the Euclidean distance between 2 points, x and x star. Okay, and I'd like the distance to be, I don't know, less than, or let's say greater than some desired distance. That's a nonlinear constraint. A nonlinear solver will do its best with that. But don't write it like that. That's really bad, right? So why is that bad? What does that function look like as if I were to just plot d, or let's write x minus x star here, right? D, then that it's going to look like this, right? As I move x away, it's going to get the distance. That should be a slope of 1. My artwork's not great, or my scale's whatever, but the derivative of the square root at the origin is singular. It's singular at the origin, right? So if SNOP just happily calling my function with autodiff, and your autodiff comes back and says nan, SNOP's going to say not happy, infeasible, bad numerical problems, or something like that. You could write exactly the same constraint. Like this, okay? And then the thing that SNOP has to see is this, centered and whatever, okay? Then it's got a constraint on d squared instead of on d. Fine, okay? But this is now a nice landscape for gradient-based optimization. Okay, so even though you can write anything in here, your solver will like you more if you write things that have nice gradients everywhere, right? That are conditioned nicely. Don't have things that have, technically have gradients, but they're like super steep gradients or something. Just as an example. But there, you don't have to just memorize all the tricks. I mean, a little bit, but another thing that the solver using a solver front end can give you is that there's a lot of distance functions and the like that we use all the time in robotics, and kinematics functions and whatever. And we try to make nice implementations of all those constraints for you so that you don't have to remember all the tricks and that. So there's a long library of there's mathematical program cost and constraints, which are the add linear cost, add quadratic cost. But if you go into the multi-body world, or even just in the, there's this whole list of costs and constraints, you can talk about what's the right way to talk about the angle between two vectors, or the center of mass position, or the distance between two things, or the gaze target constraint says I've got some kinematics of my robot and I want the cone that comes from my perception system, I want my hands to be where my cameras can see. And these are they all have particular forms that kind of get worked out, and you can make good choices here to make the optimization better. So if you leverage those constraints, or just read those constraints and learn the tricks, but these are kind of nicely implemented, thoughtfully implemented versions of those constraints. And we use those heavily, in the DARPA challenge. We have, even in the simplest case of just doing inverse kinematics, not even trajectory optimization, we have this interface where you can say, I want your hand to be here, but I want your feet to not move, right? You want your joint limits, you have your collision avoidance, all these kind of constraints, and we just have this library of constraints that you can add to the optimizer and let it do things in real time. This is the funny version of it. So I don't know if anybody remembers the DARPA Robotics Challenge. There was this scene where we have an enormous humanoid and it had to drive a small car. And the government furnished the humanoid and it furnished the Polaris. And I was like, why did you give us a robot that's too big for the car? Okay, but, and we had to even get into the car, drive the car, get out, and then go to the disaster response scenario. So the only way we could figure out how to fit this, so it didn't fit behind the steering wheel, okay? So our optimization tools, we realized that if you sit kind of between the two seats and your left foot goes over the console and drives with this, and you drive with your left hand, and you kind of look out the window like this, okay? But it was a big, complicated optimization that found the solution to that, right? And then, my God, getting up, having to get your foot over the console, while you're a humanoid robot, not cool. But that's how we drove. From the passenger seat. All thanks to optimization. Yeah. Yeah, I don't know. I really couldn't tell you. I mean, I think I probably there was a good reason, but to us it never made sense. Yeah. There were other humanoids that were smaller, but the Atlas teams had a hard time with that. Yeah. Okay, you can also, there's a whole library of constraints. One of them I mentioned actually quickly was this collision avoidance constraint. So let's say you're a quad rotor. This is before Skydio gave me the artwork. And you just want to like avoid your polygonal trees, right? Those are, again, nonlinear constraints that you can add to the solver, saying the distance between my quad rotor and the trees has to be greater than some distance. But you want to be very thoughtful about the way you implement that kind of constraint, okay? The picture I like is sort of a simple plane flying through a polygonal forest, okay? Let's just appreciate for a minute what has to go into writing that constraint well to make it scale and to make it numerically good for the solvers. Because I think it's a good window into the sort of the world of non-convex optimization. So let me just say kind of maybe a simple version of that. Let's just say I was a cart pole, okay, or even just the cart, the double integrator here, my decision variable x, and let's say there's a wall here. So clearly you should say I have a constraint that's of the form x wall, right? Like this would be a linear constraint, it'd be a reasonable thing to add to the solver. You'd be surprised. Sometimes people actually, because the thing you can get when you query a collision engine is about collision or non-collision. One could write the constraint. Let's say, g of x equals 0 if not collision, 1 if collision, because this is the kind of thing you can just ask, is this point in collision or not of a collision engine? And then you could sort of say that g of x less than 0.5 or something like this, right? And that would be a very bad constraint for the solver because there's no gradient information. That's sort of clear? Right? This one says if I change x a little bit, my constraint will change a little bit. Even though there's a limit, a threshold there, it tells me incrementally how to move towards the constraint or away from the constraint. This one has hiding all that information. Okay, so the first thing to observe is when we're trying to not fly into polygonal trees, then the first thing you want is a collision engine that can tell you the distance, not only the true or false collision, but the distance to collision. So you need sign distance functions, okay? For that, okay? You want to say that the distance between these things, and it's actually, so a lot of people think about sign distance functions now with NERF and all these other things, and all the implicit representations being popular. The easy case is what's the sign distance of a point to a geometry, let's say. That's like the common sign distance function. This is a slightly more complicated one. This is the sign distance as a function of the join angles, let's say. But this is the minimum distance between two geometries. Right? So if I'm a plane, and a polygonal obstacle, red is good for bad obstacles, right? I need the minimum distance from any point on the plane, let's say, or let's say each convex piece of the plane. Maybe I have this distance and also this distance would be two possible geometries. It's easier to check sign distance between convex geometries. Okay, so anytime that there's an opportunity to split this into two different computations, it's better to do that. Okay, so you need an engine that can do that. And as you change the decision variables, let's say the position orientation of the plane, that distance has to be a function of those angles. Okay, so there's collision engines that'll do that. Drake's collision engine will do that. Other collision engines will do that. And then basically, if you say, so these are this sign distance function, we typically write it as phi, the sign distance. Why do I say signed distance? Right? It's a signed distance because I want it to be negative when you're inside the object and positive when you're outside the object. Right? 0 when you're on the boundary, you're just barely in collision. Because it's important to distinguish between being inside the object or being outside the object. If I just said distance function greater than d min, then I might be like in deep penetration and satisfy my constraints. Okay, but now let's say I have many trees in my forest and many pieces of my airplane. So suddenly now I have to think about either for every possible collision pair, maybe so for every possible collision geometry pair, maybe I have phi ij greater than just a function of q, let's say. Where I and j are like body I and body j. Okay? And then that means if I have n collision geometries, I have n squared constraints. It also means that my solver's spending time, like when there's only really a threat of running into this obstacle, maybe, it's still computing like the distance between my tail and the geometry way over there. And you don't want it to scale to big problems. You don't want to be doing that. Okay? So it turns out it's actually better to talk about not the pairwise distances, but the minimum distance. Okay? So you can do better, more scalable, to do, let's say I want the min over phi ij. This would be a minimum distance lower bound constraint. Okay? Is that fair? So let me make sure it's like this, yeah? I'm going to compute all of the, ideologically, I'm going to compute all of the possible distances. And I'm going to only take the minimum one, and the minimum one had better be bigger than my minimum distance. Yeah? I'm saying for all I, so this would be minimum over all possible I and j. I could say min maybe would be clearer, but I wrote it. The geometry pairs. So if I say geometry I, j, so for every body I've registered with my collision engine, I'm going to call that, it could be body I, right? And I'm going to loop through, for every body, I'm going to look at through all the other bodies. Those are the body j's. Every pair, so it's a total of n squared in the worst case. Yep. Yes? Yes, that's awesome. That's exactly that's what the solvers do, basically, is a kind of a two-stage collision checker. So it's typically, it's not quite as smart as that. Like if you had a deeper integration between the solvers and the collision engines, then I think we would do exactly that. What we do in practice is we set a threshold beyond which we're going to ignore collisions when we ask the collision engine. Okay, I'll write this down in a second. But we basically say, tell me all the collisions closer than a meter. Okay, and then I'll evaluate this min over those. The solver doesn't know we're solving a minimization problem, and it doesn't know it could terminate early if I found a small distance. The collision engine doesn't understand that. It could if you wrote a more integrated collision engine, but typically that's not a query it knows how to answer. But it does know how to do broad phase collision checking, it's called. So typically it's not done with spheres, but with axis-aligned bounding boxes. And you can quickly find an outer approximation of the distance with axis-aligned bounding boxes, and then prune away a lot of the i's and j's. Yes?
Is
Yep, exactly. So the axis-aligned bounding boxes are essential to make, any broad phase collision it makes things scale in simulation also. Exactly right. Yes?
This is just scalable more in terms of the optimization. We are still doing the computation over all the phases.
Nope, we're going to write one constraint now. And the decision variables were always like the configuration. That hasn't changed. It's just that the number of constraints went down, but each constraint got more complicated.
Yeah, that's what I.
Yes.
Like we made it more scalable in terms of the number of constraints, so like the optimization is more scalable.
Yes.
But we're still doing the same number of distance calculations.
No, because of what she was just pointing out is that if I tell my collision checker, I can do a two-phase, effectively a two-phase thing in my collision checker. I can say, and what it is in, I actually wrote it down here. You'll see that you can basically ask the collision engine, give me all distances less than some threshold, an influence distance. So you do a signed distances less than some, we call it influence distance. And that allows you to prune out a lot of possible collisions, or just compute very proximately with axis-aligned bounding boxes. And you don't spend time accurately computing the hard geometry problems. Okay. Now, you could potentially do that. You could potentially do that interleave that more into the optimizer, but then the number of constraints could change dynamically, and you don't know a priori. And so it's traditional to do it, tuck that into a constraint. Yeah? But there's more subtlety still. But wait, there's more. Taking a min over these functions is actually a lot like this, right? It could be that even though the minimizing distance should be continuous, it need not be smooth. The moment where body A and body B used to be close, I changed a little bit, suddenly now body B is closest to body C. That can cause landscapes that look like that. So min, in general, is a scary thing to hand to an optimizer. You want to do like a soft min or a soft max, okay? In practice, we take these hinge losses. You'll see like a lot of work in the collision query to give you this, like, you have your distance, you have a function that kind of goes down like this. This is here is the influence distance. Here is the minimum distance. Make that equal to 1, or cross at 1, okay? And then you want this to grow roughly linearly for good numerics. Okay, so basically we push the distance computation through this hinge loss to make it nice for optimization. And then we do the hinge loss, if you will, of the distance should be greater than, less than, equal to, should be greater than 1. I wrote that wrong in my notes. And then you do a soft min of the hinge losses of Q is, for your optimization. It's just to say there's a lot of stuff going on that people thought carefully about to make the landscape as good as possible for some of the hairy constraints that you run into in multi-body optimization. Okay? And they are for performance reasons, and they're for optimization numerical reasons. So you should write it yourself once, hit that hardness, appreciate it, and then call the solver, and then not have to worry about it. Yeah. Yes?
So we no longer have this property where the space of position variables that were optimized over context.
Great. Collision avoidance is sort of the classic problem where you have non-convex optimization, right? So if I have my super high fidelity graphics airplane, right, and I have a trajectory I'm considering that's like this, and the actual optimal solution is over here. This is exactly a canonical example of non-convexity, because the solution has to get worse. If you want to deform this with gradients to the true optimal solution, it actually has to violate a constraint before it can pop out the other side. So this is like a strong local minima. And in general, the non-convex optimization is going to, it might get lucky and hop over there with a big SQP step, but for the most part, it's going to find a path and it's going to optimize within that path, and it's unlikely to then start examining another path unless your gradient step size is bigger than you expect. Yeah, it's a great example of non-convex optimization. Yeah? So trajectory optimization, powerful tool, great for projects. And historically, like a lot of projects have used trajectory optimization, but there's some frustration that goes along with it. So it's a bit like, so when the solver's working, it'll do amazing things and you'll be happy. And then if the solver doesn't work because it's stuck in a local minima, it's very frustrating, right? So compared to like the tools we've talked about so far, it is capable of doing great things, but gives no guarantees. There are, one of the topics in research in my group is trying to make that more bulletproof, for instance. But okay, let's talk about stabilization. Yes.
More or less frustrating.
It's a fair question. It's a good question. So the question was more or less frustrating than reinforcement learning. I think they're frustrating in different ways. I think the cost function and constraint tuning. So if you put everything in the cost function, then it's very similar to RL in some sense. The language of having rich constraints, I think, can make it a little bit better than RL in that sense. Some things are naturally described as constraints. And if you're putting in as a penalty in the cost and starting to tune penalty weights and stuff like this, then it's worse, I think, in that sense. The other, I think these experiments run in a few seconds, and RL can, depending on how fast you've optimized your pipeline, RL can take longer to tell you if it worked or didn't work. So I think this is less maddening, but it gives you less also. It gives you a trajectory, not a policy. RL people should feel free to push back on that if you disagree. They're similar, yeah. Okay, so it gives us that's a good lead in. It gives us a trajectory, not a policy. How do we turn that into a policy? Okay, so let's think about trajectory stabilization. So you guys, if you had given me like these questions that make me talk about, robots from 20 years ago or something, you might have gotten out of having to know trajectory stabilization for the midterm. But I got you. I made it, and now it's on the midterm. I would have considered it a failure on my part if I didn't get to it. Okay, let's just think about, like, say, the acrobat swing up, okay? So if I do trajectory optimization, I get some nice trajectory. I get some decision variables x and u that come out of the optimizer. It does an impressive, swing up and balance. If I did direct collocation, then I even have like a continuous trajectory defined for all time, between 0 and t final. And that used constraints that were imposed by some numerical integration approximation. And if you put it in exactly the same simulation, exactly the same initial conditions, and you simulate it forward, but with a different integrator, you will see that it does not get to the top, right? It'll depending on how closely, how finely you discretize time, you'll probably see it go like this and just wonk and just fall down, right? So certainly if you have uncertainty about your model or random initial conditions or something like this, you definitely need more. But it turns out even just to make it playback in simulation, people will talk about, if you say, here's my trajectory optimization, people will ask you, is that a planned playback or is that a simulation rollout? Because those are different. If you can show that you've stabilized it, then you've done something more. So the question would be then, how do you stabilize the trajectory? Now, I actually don't like using the word stabilize for finite horizon things. Stability is about going as time goes to infinity. But rather than introduce new language, I'll use that today, but we're going to get to time equals infinity. I want to track the trajectory. We've already talked about one idea, which is model predictive control, right? So if I can solve the original trajectory optimization fast enough, then as I get to a new initial condition, I can just solve it again to the end, and that could definitely work. That is a dominant approach. But we also talked in model predictive control about trying to guarantee recursive feasibility. And if you have a nonlinear trajectory optimization, then with no guarantees, then you typically cannot guarantee recursive feasibility. So for instance, in the DARPA Robotics Challenge, we had great trajectory optimizations of Atlas running and stuff like this, doing more dynamic things. We did not use any of them in the competition because I didn't want Atlas to be running around and then be like, oh, SNOP says failed to find a solution, and then, we weren't willing to risk it, right? And I don't think you'd want to risk it on an autonomous car or airplane or anything like that, right? So, but I want to distinguish, MPC is used all the time on cars and planes, but let me just make a super important point here. There's a difference between the trajectory optimization that we're talking about here, which is trying to solve like a very global solution. It's trying to find a path through the forest, polygonal forest to the goal. There's a very different optimization problem, which is I have a nominal guess of the trajectory, and I just want to get back to the trajectory. The landscape can be completely different if you're just stabilizing a trajectory versus trying to find a trajectory out of thin air. And in that regime, we can start talking about having guarantees that a solution should keep coming out of the solver, recursive feasibility. Okay, so stabilization is different, easier, let's say, than the global optimization. And it turns out you don't even need model predictive control necessarily. I want you to think about model predictive control. I already introduced it as model predictive control is kind of the generalization. Let's say linear model predictive control is the generalization of LQR to handle constraints. And even for stabilization, in the stabilization regime, you should think of it again as a slight generalization over what a linear controller would do to stabilize a trajectory. Yeah. Yep. So, the question, so if you were to do model predictive control, then I say you have a policy. But the solution to a single trajectory optimization is only defined for the x's that are on the solution, which is the point, is that you don't have to explore all of state space. That's what lets it scale. If you can solve it robustly on the fly, then you have a policy. Okay, so the key idea here is the idea of linearizing around a trajectory. Just like we linearized around a fixed point, let's talk about linearizing around the trajectory and think about stabilizing the linearization. This is something we can do guaranteeing, with nice guaranteed properties, okay? And it's the way to sort of separate out, I have to find a different path around the forest from, I just want to get back, where life is good and the dynamics are smooth, I just want to get back to my trajectory. Okay, so you remember we talked about the linearization of the pendulum. I had the theta versus theta dot phase portrait for the pendulum. The linearization of the pendulum looked like this, right? It had this nice, and it followed the nonlinear dynamics impressively well, close to the trajectory. That was when I linearized around to the fixed point here. And we got the question right away during that lecture, like, could I linearize around some non-zero velocity, let's say, some other point, right? So trajectory optimization is now going to give me trajectories. Let's say it gives me one that swings up from here and it does something like this to get to the top. And I want to stabilize that. So a natural question would be, could I linearize around that point? Let's call that some x nominal, and it's going to have a u nominal associated with it. What happens if I linearize around that point? And notably, theta dot at that point is not 0. Okay, so I have what happens in the mechanics of doing that. I have x dot equals f of x u. My Taylor approximation is f of x nominal u nominal where this is evaluated at x nominal equals u nominal. Right? That's my Taylor approximation. And one of the things we did before was we leveraged the fact that at a fixed point this was 0. Right? It used to be 0, but now it's not. So in fact, we don't have a linear system. At best, this is kind of an affine dynamics approximation. You could argue that maybe MPC, I could write the affine constraints, but it turns out there's a better way to think about it. Okay? So here's the way to think about it, is linearizing around a trajectory. Let's define x0 of t and u0 of t. And we're going to do exactly the same Taylor approximation. That hasn't changed. But the key point is that I'm going to define my error coordinates. Remember, we always wrote ourselves relative to the point of linearization as x minus x0 of t. And u bar is u minus u0 of t, which is a little strange, right? This means you're in a time-varying coordinate system. The origin of your coordinate system evolves forward with time. If you sat still, the coordinate system is moving away from you, and you're in the error coordinates, you're not going to stay at 0. If you are at 0 to begin with, to stay at 0, you've got to move along the trajectory. Yes?
So is the idea that at time t, you're linearizing around
Yes? That's a super important distinction. So I am only linearizing on the actual trajectory. There's a refinement, but has to be done carefully later, which says if I wanted to project to the closest point on the trajectory, how do I do that? That's not what I'm doing right now. Purely as a function of time, I'm looking up into the index and saying whatever x is at that time, that's the point I'm looking at. Good question. Okay, if you do this, now x dot equals f of x 0 of t, u0 of t. You can call this x dot nominal of time. I don't mean it to look, it's not surprising really, it's just I'm just writing it in the proper coordinates, because in this error coordinates, this is just x bar dot equals a x bar plus, well, almost, let me be more careful. In the error coordinates, it is again a linear dynamical system. Yeah? You go. This should also have a t. Yep, still the nominal trajectories. And these are still evaluated at any time. Yeah? In this moving coordinate system, even when I have non-zero velocities, I can get a time-varying linear system. It's time-varying, right, because the A matrix, which is this partial f partial x, is evaluated at different x's as it moves through time. So what we need to do is understand how to do optimal control for time-varying linear systems. Right, which is, it's like a totally different class of systems in one mindset. Like the things that can represent are not just like this local thing. It's like this, it's potentially, you can take a nice approximation of very rich nonlinear dynamics with time-varying linearizations. But it turns out linear optimal control can crush this problem too. Right, that's in the space of things that we can mostly just solve. So it's a very powerful extension. It has its limits, but it's a very powerful extension on the original formulation. Okay, so to see that, let's do the LQR version of that. To see that, let me actually first, I'll do finite horizon LQR. Even without the time varying component. Let me just remind us sort of the finite horizon extension of the original LQR problem. Okay, so that was, I would write that as, I'm going to minimize over my u's the integral of standard assumptions x dot equals a x plus b u. I have not added the time varying aspect yet. The only thing I changed compared to the one we've used the whole time is that now it's not infinite horizon, it's finite horizon, right? So this is the change. I could add also a terminal cost on there if I wanted to, but I'll keep it simple. It turns out the solution to this is almost exactly what we wrote before, but now it's a time, because we have a finite time, that sends ripples through the cost to go, basically, and the cost to go function now is a function of time. Even if all the problem data is not a function of time, just having a finite horizon means the optimal action right before the end of time is different than the optimal action far from the end of time. So it turns out the optimal solution is still a quadratic form. It's just a time-varying quadratic form. And the optimal policy is just like this. It's a time-varying gain. And the way you find S is a little bit more interesting. It's almost the same Riccati equation. So the original Riccati equation that we solved just had a 0 on this side. Okay. I should say that the Bellman, once you have a time varying thing, this is coming from the Bellman equation, which is the min over u of L of xu plus partial j partial x f of xu plus partial j partial t equals 0. There's an extra, once you have a time dependence, you have a time dependence in your Riccati or your HJB also. This is the Riccati differential equation. In some sense, it's the more fundamental thing. In fact, the infinite horizon Riccati equation, like I said, it's setting s dot equal to 0. It's just the infinite, it's the stable solution to this equation. If you were to simulate this backwards in time, it will stably converge to the infinite horizon solution. Typically, you'll put the boundary value problem, the solution at the end of time, and you simulate backwards. So the only thing I changed from the LQR derivation is this time. And the math went almost exactly through, but I just picked up it's a time-varying cost to go and a time-varying gain. Okay? But here's the amazing thing. Everything in the derivation also goes through if A is a function of time, if B is a function of time, even Q and R can be functions of time. The solution is just, you integrate now a time, even more time varying Riccati equation to get the solution. LQR also works for time varying linear systems. Okay? So a very good, reasonable way to stabilize a trajectory is to take a time varying linearization around the trajectory and then do LQR along in the vicinity of the trajectory. Okay? Yes?
There is going to be some.
Mm-hmm. Awesome. So in fact, everything you just said, which was about the error could build up over time and your linearization is only good around the fixed point, for instance, that's actually all true even if you're linearizing around a fixed point. Okay? It's almost no different. Like if you just, so one of the reasons we like having x transpose qx in the objective is because it tells you to try to keep x small. That's where your linearization is good. The same thing is true when you're moving along a trajectory. By virtue of having cost on the x, it's saying stay close to the trajectory. That's where the linearization is good. And just like we had sums of squares to find regions of attraction to know where the linearization is good for the time invariant case, we're going to be able to do sums of squares along a trajectory. That'll be my fun thing on Tuesday, yeah. And we'll be able to understand what these swaths of state space that exactly answer precisely answer the question, or at least an inner approximation of that question is how far can you be and still get to the trajectory? Yeah.
So there's a series of controls you need to use throughout the entire trajectory, and then you want to add another control at every time step to stabilize it on that trajectory. You just add them together once you calculate that?
So if I do it in now, if I do the same thing, I use the time varying linearization in the error coordinates, then the controller I get looks like this, okay, which is equivalent to u of t equals u nominal of t minus k x minus x nominal of t, if I write that out. So that's exactly how it enters. Yeah.
And that's fast enough to do it, I guess it depends on your time step.
The Riccati solution can actually be solved offline. And all you really have to implement is this. It's a few matrix multiplies online. Let's contrast that. So once you have this mental model of I've got a swath of trajectory, I'm going to take a linearization I'm going to approximate the dynamics, but in a moving coordinate system around here. I expect my linearization to be good in the vicinity of that trajectory. And by doing optimal control on that linearization, that's the way of solving a simple problem, just getting back to the trajectory with a linear control, as opposed to this hard problem of finding the solution, the needle in the haystack. Okay? If you now have constraints, okay, then the natural generalization of LQR with constraints that you can guarantee recursive feasibility and everything would be to take the linearization still, but do linear MPC to stabilize the nonlinear system. Yeah? So then you start getting into solving quadratic programs on the fly. I still think that scales beautifully for complicated systems, but that's start where you do a little bit more computation, but you can solve for the constrained version. There's plenty of applications where this actually works. You're saying I should always use MPC. This is useless. That's kind of what I mean. Not, you weren't being negative, but yeah. Yep. Yeah. So we ignore that stuff. No, I'm just kidding. No. I think the hope is that you do. No, that was a bad answer. All of those can be beautifully accommodated in our mathematics, but you want to be. I think you do fundamentally want to be doing control in like nice, smooth areas of your space. When you're right at the limits of performance, I think you must take into account control saturations and stuff like this. But actually, for a lot of nominal performance, I think you're not actively on the constraint, right? So it just depends how much you're pushing the limits. Like if you're doing stunt driving, up on one wheel, you need the constrained version. If you're just driving, Miss Daisy, then it's fine. Yeah. Yes. Okay, good. So it can be solved once you have your trajectory. So and we'll talk about this more, but there's a lot of approaches that will compute trajectory libraries and pre-compute Riccati